Hello APC Mechanics student, today we will solve the past paper of RQ 2021 set 2, exercise 3. Now usually the figure always appear before the text or the question itself. Then 3, a block of mass m is placed on top of an ideal spring of spring constant k. The block is pushed against the spring, compressing the spring at distance delta x. The block is released from rest, which means that the initial speed is 0. Leaves the spring at the position shown in the figure. It travels upward and enters a track with a constant radius of curvature r that has a negligible friction. So the moment there is no friction, which means that we can use the conservation of energy. The block enters the track at point A, maintains contact with the track, and exits horizontally at point B. This is very important. While the block exits horizontally at the point B, which means that theta is 0, which means cosine theta is 1, which means sine theta is 0. A distance 3r above the point the block was released. The block then falls to the ground and lands a horizontal distance d from the end of the track. Express all algebraic answers in terms of mk delta xr and physical constants as appropriate. The size of the block is much smaller than the radius of curvature of the track. Then let's start with part A. As we anticipate, usually the first part would be an FBD. On the dot below, which represents the block, draw and label the forces, not components, that act on the block while still in contact with the track at point B. Each force must be represented by a distinct arrow starting on and pointing away from the dot. And as you notice that here we have an additional instruction, which states that we need to justify the choice of the vectors, which means we need to explain why we have represented these factors in this manner. Alright? Then the FBD can be drawn at any instant along the motion. They are interested in the FBD at the point B, so that's the block. What are the forces that might be acting on the block at this particular point? The block has a mass, it will be subjected to the pull of gravity, which is down. And because we have a support at this point, and it is horizontal as mentioned in the text, then we have the normal push, which is downward. So let me represent the pull of gravity, which is down. And the normal push now here in the question, if you notice carefully, they didn't mention anything about the relative length of the vector. So it's fine if we have represented Fg to be greater in length compared to Fn, or vice versa, or even equal. Try to avoid the equal. Here it is difficult for us to determine which force is greater than the other one. Now in this case, let me justify our reason. So what about the pull of gravity Fg? Why it's like that? We might say that the pull of gravity always points downward. And the normal push is given by the fact that it is perpendicular to the support. Then that would be the justification for the choice of vectors. Now in B, idea 1, we have ideas. And then it seems that they will be related to each other. And remember that we need to derive an expression. We need to make sure that our answers would be expressed in terms of these. In additional to physical constants, we need to derive an expression for the speed v of the block at the point B. Now, initially the block started from this point while the spring is compressed. Then it will reach the point B of the circular track, and this can be done using energy. Now the thing is that we need to choose our PE level. We have two good choices. We can choose either the PE level to be the ground or to be this one. For me, I would go with the ground. You can try it as an exercise to choose the PE level to be the one passing through the compression, the horizontal compression, the horizontal level passing through the compression of the spring. So let me here take the PE level. To be the ground. And now, because this is a big law, we need to say apply the conservation of energy, apply conservation of energy. And remember that this usually they give it half a mark. Because it's a big law, always we need to mention big laws that we're using, like conservation of energy, conservation of momentum. And in this case, this point which is here, it's not being labeled by any point. So I'll say energy initial would be equal to the energy at the point B. Now, what are the three energies that we have? We have kinetic energy initial plus gravitational potential energy initial plus elastic potential energy initial. And that would be equal to kinetic energy at the point B plus gravitational potential energy at the point B plus elastic potential energy at the point B. Knowing that the block was released from rest, that would be 0. And when the block reaches the point B, we have no more springs, so that would be 0. Now, what is the gravitational potential energy initially? So I suppose that the block is here. Then it would be at a distance r from the PE level, so that would be mgr. And the potential energy of the spring is given by half kx squared, so that would be delta x to the power of 2. That would be equal to the kinetic energy at the point B, which is half mv squared. Now they have named the speed to be v and not vb, so I will use the same notation, plus mg, and the distance from here to the PE level, that would be 4r. And we're interested in determining v squared. So let me take this to the other side. That would be minus 3 mgr plus half k delta x squared is given by half mv squared, which means half mv squared is equal to half k delta x squared minus 3 mgr. And now let me divide by m. So these will cancel, and let me multiply the equation by 2. We would get that v squared is given by k over m delta x to the power of 2 minus 6 rg, because 2 multiplied by 3, that would give us 6, and let's consider the square roots. Then the speed at the point B is given by k over m delta x to the power of 2 minus 6 rg. What does the speed represent? This is the speed when the block reaches the point B of the circular track and about to be launched horizontally. Now, in idea number 2, derive an expression for the magnitude of the net force on the block at point B. Always and forever, the net force is determined, or one of the ways, by implementing Newton's second law. So let me say apply Newton's second law. Then remember that this is a law. Usually they give it half a mark or a mark. Then F net would be equal to MA. Now what are the forces? Let me state the following. Here we're interested in determining the net force. So a wrong thing you would be doing is to replace F net by the forces, because we need to determine what is F net. So if you have replaced F net by the pull of gravity and the normal push, then that won't give us the answer that we're searching for. So we're gonna keep it like that. And here, if you notice that the net forces at the point B, they're acting downwards, which is along the centripetal direction, which is along the center, supposed to be here. So now we can say projection along the center. So indeed F naught would be the same as F naught centripetal. That would be ma centripetal, and we know that the centripetal acceleration is given by v squared divided by r. So in this case we can say that F naught c would be given by mv squared over r, and always and forever. Now here r, what does it represent? R indeed is the radius of the circular track. And because this is idea 2, then the speed would be the speed at this particular point, which is the point B. Then it would be replaced by this expression that we have determined previously. So let me say F naught c would be m divided by r multiplied by k over m delta x square minus 6rg. Now we can expand, then m with m cancel, and that would be, okay, then the net forces acting at the point B would be k over r delta x square minus, now r would cancel, and we have 6mg. Now in part C, they're asking us to derive an expression for the minimum value of delta x min required in order for the block to maintain contact with the track through point B. So we know that the force which is responsible for maintaining the contact is the normal push. So whenever we're talking about the minimum value of delta x minimum required in order for the block to maintain contact, which means we're talking about the same concept about which the block is about to lose contact with the track, which means we need to implement the condition which is F naught is equal to 0. Because if we're removing an object from a level surface, suppose here we have a level surface. So here in this case, the pull of gravity, the normal push would be equal to the pull of gravity. As we start applying an upward force, the normal push starts to decrease, and at the moment the block starts to lose contact with the ground or with the surface, the normal push changes to 0. So we need to use the condition normal push is equal to 0. Then again, because we're talking about the normal push or the condition related to the normal push, which means we're interested in Newton's second law. So let me write F naught is ma. Here no need to mention a law because already we have mentioned that law in idea number 2. And now we need to split the net forces into the pull of gravity plus the normal push, and that would be equal to ma. Now we need to project, so projection along the centripetal direction, so along the center. Now what is the positive direction in this case? Always the positive direction is toward the center. This is the center. Both the pull of gravity and the normal push are pointing downward toward the center, so both of them are plus. Then that would be plus mg plus Fn equals to ma, and already we have determined the expression of A, which is given by v squared over r, which is basically this expression. Now let me say loses contact that means that the normal push should momentarily vanishes, then mg plus 0 is given by m v square over r, that would be r, and v square, let me just copy it, that would be k over m delta x square minus 6rg, and indeed we're searching for delta x. In this case delta x represents the minimum value. Now let me continue my work here. So mg is given by m divided by r multiplied by k divided by m delta x square minus 6rg. Now m with m cancel, I can take r to the other side. I'm just isolating for delta x, then rg is given by k delta x square minus 6 rg. Now taking this to the other side, which means k delta x square is 7 rg, then let me write it down. K delta x square is 7 rg, which means delta x minimum, the minimum required value for delta x in order for the block to make it to the point B before it loses contact, is given by 7 rg divided by k. And here let me do a check on all the derived expressions that we have done so far. Don't forget this step. We need to express in terms of mk delta x and r. So indeed mk delta x and r, the fundamental constant, that's good. Don't expect that they will tell you to express in terms of radical or power 2 or the negative sign, because these are mathematical operations. K delta x, m and r, fundamental constants, accepted. K, r and g, accepted. So also let me add the following command. You might not use all the quantities listed in the question itself. Now in part D, the procedure is repeated several times with distances delta x is greater than delta x min. So why this condition at this point is important? In order for the block to make it to the point B and continues its path, and we know from point B to reach the ground, the motion will be projectile motion, neglecting a resistance, neglecting frictional forces. It will be acted upon the pull of gravity. Now we are interested in determining the value of D. This is straightforward, because from this point, because this is horizontal, then which means that theta is 0, which means cosine theta is 1, which means sine theta is 0. We will choose the origin to be this point. Now x in this case is given by the equation of motion for a projectile, which is given by x is x0 plus v0 cosine theta t. Now the first step is to identify what is x. X in this case would be capital D that we're searching for. Now that would be 0, that would be 1, and v would be the speed at the point B, which is given by v from part B idea 1. Then D in this case would be given by vt. So remember that this horizontal distance would be replaced by x. Now in order to get t, we should refer to the vertical position, which is given by y is y0 plus v0 sine theta t minus half gt square. Now here, why do we have a minus sign? Because we're always considering the positive direction to be up. The origin is set on the launching point. That would be 0 because sine theta is 0. And y in this case, this is a bit tricky, because our positive direction is up, then y would be negative. But what exactly from this point to this point, which is a metric measure of 3r plus r. So that would be exactly equal to, so here we have minus 4r, then minus 4r equals to minus half gt square. And if you isolate for t, t would be given by the radical of 2 multiplied by 4r divided by g. Now why I have represented in the following form, just to clarify that it is indeed given by the radical 2h over g, which is given by radical 2h over g, which is itself 8r divided by g. Now we have the expression of t in terms of r, and v already have been predetermined by k over m delta x square minus 6rg with the radical. Then in this case we can directly say the distance d, which is given by the speed, which is the radical of k over m multiplied by delta x square minus 6rg multiplied by the following factor 8r divided by g. And now in part E, the graph below shows the best fit line drawn by the students through their data of d as function of delta x. Alright. Explain why there are no data for section 1 of the graph. Now notice that we have calculated delta x minimum, and delta x minimum represent the minimum value of delta x such that block B maintains contact with the circular track. Or another way, it's the minimum value required from the spring in order for the block to make it through the point B. Because for values less than that, the block won't make it through point B and we won't have any projectile motion. So for this reason, for values delta x less than delta x minimum, we could not collect any value. Then let me say the following. Since the block needs a minimum speed to make it through B, then no data could be recorded for section 1 because the compression of the spring does not produce enough speed to make it through B. And now finally for idea number 2, explain the reason for the shape and minimum value for section 2 on the graph. So let's start with the shape. They're asking us to explain the reason for the shape of the curve for section 2. Now if you refer back to the previous expression, which gives us the function of d and delta x, so delta x is to the power of 2 and here we have a radical, then the square root, let's assume it cancels to the power 2, which means that d and delta x, we're talking about d and delta x, they are linear. For this reason we expect that the variation would be linear. Then let me say that from the equation in part D, D is directly proportional to delta x, then the graph would be linear. Now here, as for the other part, which is the minimum value, we discussed it already. We said that this is delta x min, which produces enough speed in order for the block to make it through the point B, and by that we can register a minimum horizontal distance covered by the projectile. So let me state it. The minimum value is the distance traveled by the block when the compression of the spring generates the required speed to make it through B. right? Then that's it for me in this video, guys. See you soon in a new one.